This CPS project is directed by co-PIs Professors Jose and Matthew at the University of Michigan. Here's a brief outline. In this video, I'll discuss our project's objective, application, proposed methods, and preliminary results. Our objective is to develop scalable methods of controlling large collections of subsystems to achieve a common objective while ensuring safety constraints are satisfied. The three terms that are highlighted are key characteristics of this problem and will reappear throughout the talk. So on to the application. Our application is load control for power system services. We control thousands of electrical loads, such as air conditioners and electric vehicles, to help balance the supply and demand of energy on the transmission network, subject to safety constraints. There are individual constraints to ensure load safety, such as an electric vehicle battery's state of charge, and there are group constraints to ensure distribution network safety, such as the safe voltage ranges. So on the left, you can see, lower left, you see a distribution network where each node is representing 5 to 10 households. And in the lower right, you'll see the nodes in red have voltages that are below the safe level. And this is what our group constraints will be designed to avoid. So next we'll develop a model of the control plant, which in this application will be a collection of air conditioners. On the left is a diagram that shows an air conditioner's state. The state is determined by whether the air conditioner is on or off, and the temperature of the space that's being cooled. When an air conditioner is off, it moves through the temperature space, shown here. So the temperature is increasing until it hits its upper temperature limit, at which time it turns on and the temperature begins to cool down until it hits the lower limit, at which point it switches back off. So theta is the temperature of the space being cooled, and on the right is the air conditioner's temperature dynamics, which are described by two differential equations, one for each discrete mode. We're actually interested in controlling a group of air conditioners, which we can show here on one state diagram. And we're looking at heterogeneous air conditioners, which means that they move through the temperature space at different rates. And just to introduce some terminology, a group's on count is the number of air conditioners that are on at a particular time t and is denoted with capital K. So now that we have the model of the loads that we're going to control, we'll discuss the proposed control methods. So here is our control architecture. We can divide it into three categories. The first is the upper level tracking controller, which is designed to achieve the common objective, which is to track an energy balancing signal. In purple are the lower level safety controllers, which are designed to ensure the safety constraints are satisfied. And in blue is our large collection of systems, in this case, air conditioners. So in the next slide, we'll go into detail on what's happening inside of the safety controllers. So the safety controllers have two tasks. The first is to identify safety constraints for the distribution network, and then the second is to ensure those constraints are satisfied. So on the left is our distribution network diagram, and node 20 is highlighted. An example of a safety constraint for node 20 might be that no more than 5 air conditioners can be on at one time, otherwise the voltage constraint will be violated. So more formally, we call this a counting constraint with a lower and an upper limit. And we won't go into too much detail about how we determine these constraints in this video, but we will talk about how we ensure the constraints are satisfied using an algorithm we call mode count control. And we'll present the algorithm through an example. So in this example, we have 8 air conditioners and their on count must be maintained between 3 and 4. Air conditioner E is about to hit its upper temperature limit, so if we switch E alone, it will violate the counting constraint. So we have to determine which air conditioner to switch off to counteract E switching on. We do this by ordering the on air conditioners in terms of time, specifically the time it will take them to reach the upper limit once they're switched off. You can see here that C has the largest time to upper limit, and that is the air conditioner that we will switch off. So to summarize, we switch E to satisfy its temperature constraint, and we switch C to satisfy its counting constraint, or the group's counting constraint. So that's the algorithm in a nutshell, and we'll demonstrate our methods with some preliminary results. So the tracking performance of the control system is quite good. You can see in bright blue that the power consumption of the full collection of air conditioners tracks the balancing signal very closely. There's a gray line representing the air conditioners that are being controlled by the safety controller, and we'll have to zoom in to see what's happening there. So there are 3 air conditioners that are under safety control. And here the y-axis is the on count. And in purple, when the mode count control is active, the on count upper limit, which is 2, is always satisfied. So the safety controller is successful in keeping the limit, in maintaining that limit. And the effect is that the network is safe. For the node that these air conditioners are attached to, the voltage shown in purple is always above the lower voltage limit. So just by controlling these 3 air conditioners using mode count control, we've ensured that this voltage limit is satisfied. So that's all we have time for. To learn more, here are some of the publications that have come out of this project.